All right, I've just been reminded that this is the worst day in the world for me to possibly go over, since there's a very important event happening at 4. So um, let's make sure that we are crisp and in the right frame of mind for the World Cup. So uh, I can't believe how much time is elapsing, already up to my fourth lecture out of 5. This has been quite a thrill, and it's also really fun to be following today Stefan Hild, whose lecture I really liked. I hope you saw that we were dovetailing pretty well. He saved me the trouble of trying to say more than I understand deeply about radiation pressure noise. Um, and let me tell you what I do want to do. The very first topic that I had planned to do whenever I spoke today, either this morning or this afternoon, was explain how we talk about physics, especially mechanics, in the frequency domain. Stefan assumed that you knew that. That's okay. You can mix everything up that you heard today in a mélange, and you'll understand it all in retrospect, even if it went in the wrong order on that. Yesterday we talked about the frequency domain some. This is the aspect of the frequency domain that makes it so charming, that makes it so compelling to think about doing physics in the frequency domain. So I hope to share my enthusiasm for that. And we'll do a few examples, two main ones. Seismic noise and seismic isolation in particular lends itself tremendously well to frequency domain discussion, as does thermal noise, which has really some profoundly interesting physics. You're getting all the really interesting physics about radiation pressure noise from Stefan, but I'll make sure that you see it in the frequency domain context here today. So, what do physicists do when they want to analyze a canonical, easy to think about example system? We always pull out a simple harmonic oscillator. I used to just take this for granted, but once when I was at MIT, I sat in on a systems thinking class taught by a mechanical engineer, and whenever he needed a canonical example, he said, consider an internal combustion engine. And he wasn't making a joke. He thought that was the simplest system he could use as a reference, but I'll be true to form and talk about a simple harmonic oscillator. And this one in particular, let's make sure we see all of the features. A mass on a spring, okay? And we want to pay attention to the center of mass coordinate of that mass. But here's something that maybe will strike you as something you don't always do. We're also going to pay attention to the coordinate of the top end of the spring. And this is especially suited to asking the question, if this end of the spring is rigidly attached to the ground that's shaking, how much shaking gets to the mass, where this might be standing in for the mirror. So in a moment you'll see why I want to say, okay, this coordinate will take to be the input to our system, and this will take to be the output. All right, so the way I was taught to do physics, I imagine this is the way you were taught to do physics as well. Write down the equation of motion of the system, basically Newton's law for this system. So we have ma is equal to the forces which used to live here. I've moved them over on the left-hand side. So this is the force from the stretching of the spring, which comes from the difference between the center of mass coordinate of the mass and the coordinate of the top end of the spring. And I'm including something that we don't always bother to do, but it's a really good idea, a damping term here modeled as velocity damping. By the end of today's lecture, I'll complicate our discussion about damping and show you about other models. So here's the equation of motion, and the way we're usually taught to deal with this is saying, okay, it's a linear differential equation. Let's come up with the function let's come up in the time domain with functions that represent possible solutions. But what I want to do is something different. I want to propose that, at least at first, we consider a particular form for the input, and let's pick that form to be a sinusoid with a frequency f and an amplitude that I'll write as capital X sub I of f, and I'm artfully choosing notation that later on will look like something else, but for now just think of this as an amplitude that might be different at different frequencies, but we're going to be analyzing this one frequency at a time. Now, because the system that we're analyzing is a linear system, there's a wonderful theorem that says if you apply a sinusoidal input to a linear system, its output is also sinusoidal at the same frequency. And the physics is in how big is the amplitude of the output and what is the phase relationship between the input and the output. So we'll be interested in an amplitude ratio, the ratio of x out to x in, and also a phase. And it's far from guaranteed that things will be in phase. In fact, there's always, or almost always, interesting phase relationships between input and output that we'll have to learn. So, but for now, we're just going to plug these in as an ansatz to the equation of motion. But before I plug them in, I want to remind you of some simple relationships, some simple time derivatives of those complex exponentials. That if I take the first time derivative of e to the I 2 pi f t, I get I 2 pi f times e to the I 2 pi f t, and the second time derivative gives us a minus 2 pi f squared. Okay. So if here's that same equation of motion, but now I'm going to plug in the second time derivative of my ansatz here, plug in my ansatz for x output and x input, and this first time derivative there. Here's what we've got after canceling the common factor of e to the I 2 pi f t. And now we're almost done. We just we rearrange terms so that we can find the ratios of this amplitude of x output at that given frequency to x input. And that ratio is given by this very simple function. And that is, in fact, in the frequency domain, the way you solve that differential equation is find the complex ratio of the output to the input. So there it is again. And let's see how wonderful this is. I can think of at least 3 reasons that this is truly wonderful. All I had to do was some algebra that is so simple, I can do it. Okay? And we got what I claim is a powerful solution if only we know how to interpret what this means. And in particular, in a moment, I will explain how you can look at this object, which Stefan was calling the transfer function, and I often call it that. Sometimes it's called the frequency response, and I'm told that sophisticated people are supposed to call it that, so I may do that from time to time. When you look at the properties of this very simple function of frequency, you can get a tremendous amount of insight into the dynamics of that system that I don't know where it's available in the time domain solutions, quite honestly. And a third thing that's truly wonderful, if I have several systems to one whose output becomes the input of a next system and so on, under a wide range of circumstances, the cascade of several systems has as its total input-output relationship just the product of the input-output relationships of the individual systems. Yes, Fabian? Well, it has to be small enough that the system is linear. Was that what you were hoping I would say, or? I'm sorry? Yes, it's when I wrote it here, it could be an arbitrary function of time. By the time I plugged in here, it was a sinusoid of, in principle, arbitrary amplitude and one particular chosen frequency. Now, the hidden assumption is that it can't be so big that nonlinear behavior happens, but as long as it's small enough so that the spring is still behaving like a nice Hooke's law object, I think there's no other restriction.
Shouldn't it show up because isn't XO minus XI the stretch of our spring?
Yes.
Shouldn't it show up everywhere? Like the double dots
Well, it surely should not show up in the inertia term. The only thing that has inertia is the mass. All right. It's an open question, or it's a question of the detailed physics whether the damping should have the difference. If the damping comes from internal processes in the spring, then I should put an XI term there. The algebra is just as easy. I just didn't do it. On the other hand, this particular choice that I made represents, say, like air friction of the mass moving through, and that doesn't depend on the motion of the top. So there's real physics in that choice, but this is perfectly legit as an example. And then it's a detailed question whether you've modeled your system correctly. Okay, so I finished my solution only doing algebra. I will start to show you momentarily what kind of insight you can get. And then we have in reserve this third point, that what I'm calling filtering operations, complex filtering operations with several elements. A cascade just is represented by a product. And in case the wonderfulness of that feature is not obvious, let me state what we would have to do if we were trying to do all our physics in the time domain. If I had two linear systems cascaded, and I were trying to describe them in the time domain, I'd say, well, the filtering operation of the first one is the convolution integral of the input function of time with a function, a deterministic function of time called the impulse response. In the time domain, that's a really raunchy integral to have to do. And then if I have something else, I have to do it twice, because then I have to take that output as an input or do a whole other convolution integral. I'm just going to be multiplying functions of frequency that I can do on graph paper momentarily, and you can do it as well. So I am going to now let you in on a secret of the trade, and this is something, it involves something that Stefan was complaining about. There is a standard way that everyone learns to make a graph of frequency response functions. You must, if you want to be taken seriously, learn to draw them as Bode plots. And I will show you one, and we'll come back to the description. Here is a Bode plot, and it always has two parts. Both parts are functions of the same frequency scale. Frequency is always drawn logarithmically for reasons that will become obvious. The top graph in a Bode plot is a logarithmic plot of the magnitude of the frequency response. But to make it so that you have to be an initiate, it's not drawn with log of magnitude, it's drawn with 20 times the log of the magnitude. And that's called the magnitude in decibels. Phase is drawn on a linear scale between minus 180 degrees and plus 180 degrees. These are all conventions. I think it came from Bell Labs engineers in the mid-20th century. I'm not 100% sure of the history on that. But you must learn this convention, okay? And then you will read everyone else's graphs and know what they mean, as well as have people understand yours. So let's see, did I say everything? Yes. Two graphs, same logarithmic frequency scale, magnitude of the frequency response, logarithmic, but plotted as 20, log base 10, the magnitude, phase. Right, okay, so those are the rules, and this is the Bode plot of that function. And let me copy the function here so that we've got it handy. Okay, and I I made an artful rearrangement from that, and maybe it will be obvious why I did that. Okay, yes? For a linear system, the output will have the same frequency. Resonance or not. This is, and in particular, let's examine it for this case where there is a resonance, and but that's the beautiful thing. That's what makes this work, is that the output after startup transients. Okay, so I should say, if I want to be 100% correct, this is done in the limit that, I mean, what I'm showing you is true in the limit that I started applying the input an infinite amount of time ago, so that any possible autonomous dynamics of the system that came from kicking it at the start have damped away. Now, if I wanted to take account of autonomous dynamics that are kicked by startup transients, I should do something a little more sophisticated. I should be doing Laplace transforms, which can handle this completely well, but I think it's too fussy for most problems. Okay, but there are some problems where that actually is important. So thanks for prompting me to make that clarification. Okay, so there are a number of things we can see. There is a peak. There is a particular frequency at which the system responds much more than anything else. And remember, this is a log scale, and okay, that's 40 dB, or a factor of 100 amplification on resonance. What else do we see? For a large range of frequencies, for all frequencies below the resonance, in the limit that you get far below the resonance, the frequency response is constant, and in particular, this frequency response has unit magnitude. Above the resonance frequency, the response falls, and falls by increasing degrees at higher and higher frequencies. And you see that the response is a straight line on a log-log plot, so it's a power law, and in fact, this is 1 over frequency squared. Now, we can get this basic insight from staring at this, right? Because the limit of low frequencies, only the k term in the denominator matters. The frequencies are low, so unit value for the magnitude of this frequency response. At a special frequency, the real part of the denominator vanishes. That frequency is root k over m for a mass on a spring. That's the resonant frequency that we learn in first year physics. If I had no damping in my model would predict the unphysical thing, that the response would diverge. Sometimes the damping is very low, and sometimes for all practical purposes it's diverging and you're in danger of breaking something. Please don't. But this damping is always there at some level, and it's what prevents things from diverging. What else can we see? Oh, Stefan mentioned this as well. There is a phase shift of 180 degrees as you go through resonance. The motion at low frequencies is in phase with the input. The output motion is in phase. It is out of phase entirely, 180 degrees out of phase, and it falls through, and precisely on resonance, the response is 90 degrees behind the input, right? Now we know this, right? We all have played with harmonic oscillators or shoes. Okay, X output, X input. At low frequencies, the shoe just follows the top of the laces. So the magnitude of the motion of the output motion is the same as the magnitude of the input motion. So the frequency response is unity, and they're in phase. Okay, so we understand what's going on in the low frequency limit. Very easy for me to move the top by a small amount at the resonant frequency. So we know there's a resonance. Takes a little more practice to see that the shoe is lagging my input by 90 degrees, but maybe you can see it. I can move it a lot at high frequencies, and the mass doesn't move. I can't see the antiphase relationship with a shoe, but it's there too. Okay, so you already knew this, or at least most of this, but this is a nice summary. Now, why am I belaboring this point? Because A, a lot of things in nature are harmonic oscillators, but in particular, we use this precisely as an element, the building block of vibration isolation systems. Okay, so that's just writing on the board. If you really want to sound sophisticated, you don't say 1 over frequency squared, you say minus 40 dB per decade, and then everyone will know that you are hardcore. Yeah, every field has its own way of excluding newbies. Yeah.
To just make a comment, so those of us who've driven oscillators know you don't want to drive an oscillator doing something for you on resonance. You want to be one side or the other, right, for phase stability.
Okay, right, all right. Conceptually, though, thinking about the on-resonance case will prove to be really important. But yeah, generally, especially because we often are using very high Q oscillators, the last thing you want to do is drive a high Q oscillator on or anywhere near resonance. Okay, so that's practice in, yes, Neha. If okay, so right, so the demo I just did was horizontal. I had regionally sketched things vertically. So you're asking, does this system behave any differently? No, this has exactly the same behavior, and think of it this way. So here's my imaginary demo. I've got a mass hanging from a spring. If I slowly lift, the mass follows. If it's slow enough, the spring has got no impetus to stretch. But I could shake it on resonance, and I get a big motion of the mass for a small motion here, or I can shake really fast. But in particular, you know, picture gently lifting the mass on the spring. It will come up. It will follow your hand. Okay, so it's a property of the equation of motion, and I think it had better be because the algebra comes out the same, irrespective of the orientation. Okay, now, so that's more or less all you need to know about thinking in the frequency domain, but we'll practice on 2 main topics, seismic noise and thermal noise, and I'll have a little bit to say about at least the frequency dependence of the radiation pressure noise. Now, in all of these cases, I'm talking about important noise sources in interferometers. And one thing that all 3 have in common is that they are a kind of noise that enters the interferometer because they are actual motions of our mirrors, unlike shot noise, which has to do with the quantum properties of light. But all these other noise terms involve motion of the mirrors. And the reason that it's important to make that distinction is that, as I discussed yesterday and as Stefan discussed again this morning, it's a wonderful idea for improving the signal to noise of your interferometer against shot noise to build yourself a long optical path by bouncing off the mirrors many times. It helps you not one whit against noise that is comes from motions of the mirrors, because, okay, I think I'm building up my signal by a factor of 100, but I'm encountering the mirrors 100 times. So I've multiplied my signal and my noise by exactly the same factor. So I haven't hurt myself, but I have not helped myself at all by beam folding. So it's a very different kind of thing, and this is the existence of many such noise turns is why we invested in things as big as 3 or 4 kilometers, right? I mean, we know how to fold more than 100 round trips in an optical system, okay? But we didn't want to build something a lot shorter and just make up for it with more beam folding, because we would have had that much more trouble with these displacement noise sources, okay? So these are the real reason why interferometers should be physically large. Okay. So now I would like to say something about seismic noise, and I'm going to start by making a very approximate statement about the amplitude spectral density of the shaking of the ground, and I'm going to claim that this is close enough a description of any individual site, even though it actually does vary from site to site by not insignificant amounts. If you're interested in the spectrum from 10 hertz to about 100 hertz or so, you can represent it by saying the amplitude spectral density of the shaking of the ground is, roughly speaking, 10 to the minus 9 meters per root hertz at a frequency of 10 hertz, and that it falls roughly like 1 over frequency squared above that. I'll show you a graph in a moment. So just evaluating that, a factor of 10 above this, 100 hertz, we've come down by a factor of 100, or says 10 to the minus 11 meters per root hertz is more or less what the ground shakes at a typical spot. Is that anywhere near our target noise for our mirrors? No, it's huge. It's 9 orders of magnitude or so, too big. So if we're going to be successful at measuring gravitational waves of the small amplitudes that we think, and now we know, are out there, we need about 9 orders of magnitude seismic isolation at 100 hertz. So you can invent more elaborate specs, but for purposes of our discussion, let's just talk about a specification at that one frequency. Here is a graph. It's a very boring looking graph because I said, oh, this is just a power law. Okay, so power law on log frequency versus log displacement. So this is displacement noise in meters per root hertz. And I started at 10 hertz, and here's 100 hertz. And how applicable it is at a kilohertz or higher just seemed nice to extend it there, but I won't claim that that's horribly realistic there. All right, so this is the problem, and the other part of the problem is our target is down about where I've got the red dot right now. That's what we want. So somehow we've got to filter this noise by making this noise have to travel through a filtering apparatus between the ground and our mirror, such that that value gets pulled down to there. Yes? All right, it depends on a few things. The noise is higher near cities or near busy roads than it is far away. It's also higher in some frequencies, relatively low frequencies, near seashores compared with deep inland on a large continent. It's also higher at the surface of the ground than at an underground site. Okay, if you go a kilometer or more deep, you can pull it down a lot. So, nevertheless, what I'm giving you is something that isn't strongly dominated by human-generated noise. It's something of a sort of remote site. It's not like the hard rock center of a continent. That can be down a little bit. And this is certainly representing a surface site as opposed to underground. So there are some things you can do to find a site that reduces this, but except for going deep underground, they don't buy you a lot. They buy you a little, but the problem is basically the same. Underground, for this purpose, is a pretty good investment. Okay, is that a good enough answer? Yeah. Okay, so This is what we're staring at. We want to get to there. Now, I want us to, for this case, all we need to do is pay attention to the magnitude of this frequency response, because I want to say I want to precisely use a mechanical harmonic oscillator as a seismic noise filter. And here is an example of doing that. This one, oh, okay, this is maybe not exactly where I wanted to put the resonant frequency. Pay no attention to that exact frequency scale. And imagine that, for example, maybe this represents the frequency response, this functional form. It's a very familiar functional form. And maybe it represents a pendulum of about this length, which has a resonant frequency of about 1 hertz. So no good at all below resonance, terrible at the resonant frequency, but then once you get a little bit above the resonance, the farther you go, the better and better it is, and it improves like 40 dB per decade, 1 over frequency squared. Okay, so 1 hertz pendulum. So now here is the amazing thing about filtering operations represented by multiplication in the frequency domain as opposed to a time domain convolution integral. I'm going to take this kind of frequency response and point-wise multiply it frequency by the input spectrum, and I will find from that very simple math operation the output spectrum, that is to say the spectrum of motion of the mass at the bottom of that spring or pendulum, in response to that input. So here again is the seismic noise input spectrum, and here from 10 hertz up is my prediction for how much the mirror should move if my seismic isolation consists of a single 1 hertz pendulum stage. It's got a resonance down here at 1 hertz, but I've left that off to the left for simplicity. So this was really easy to do, okay? Just pull that line down by how far below unit transmission that frequency response function was at each of those frequencies. So anyone could do this in their head or with a little graph paper. All right, now here's my target level. I reach it at about 2 kilohertz or about 1 kilohertz here, but not 100 hertz. I'm still far away. But I'm invited to think about linear processes like this in terms of, well, let's cascade several such systems, one from another. So why shouldn't I take that original system? Why should this be rigidly attached to the ground? Why shouldn't this, in fact, be suspended by another pendulum fiber, another spring, whatever is convenient? And so maybe 2 is good. Or maybe that spring and that rigid part, maybe that's in turn suspended from something else. It's a detailed engineering question, how many times you can pull that trick, and some of that engineering is quite involved, but the principle of it is quite straightforward. And finding the answer, or the expected performance, is also pretty straightforward. So here is the basic theorem. Because those frequency response functions, the cascade of them can be represented just by a multiplication in the frequency domain, then, this is almost true, I'll complicate that in just a minute, but it's roughly true, then instead of resonant frequency over signal frequency squared, if I have a chain of n oscillators, then I should get in the high frequency limit a roll-off of 1 over f to the 2n. So I just need to I can make my transfer function, my frequency response, steep enough by having enough stages. And here is what 3 stages would do. And that meets my spec, okay? It's not very good at 10 hertz at all, but if my spec was really only be good enough at 100 hertz, wow, that's pretty cool. here is the fabulously well engineered Virgo super attenuator, and this has one very low frequency oscillator in the inverted pendulum stage. That's this as a mass on a spring represented by towers that have some elasticity down here. And now a chain of 1, 2, 3, 4, 5, 6 or 7 pendulums. How do we count them? Yeah, well, yes, here is the inverted pendulum. I get that. So regular pendulum, 1, 2, 3, 4, 5. And is this part rigidly attached to that? I'm not sure. So about six stages. And here you can see the measured input seismic noise spectrum, and I assume this must be a calculated response because I don't think you can, no one is measuring things that well. So this is a calculated response by a measured frequency response at something that was driven at high amplitudes and then multiplied. So let me retract a bit about what I said about cascaded systems. It's not simple multiplication for the frequency region where the resonances are. You have to solve a normal mode problem there because the systems interact. But they don't interact in any interesting way at frequencies that are high compared to the resonance. So here we can see this is the low frequency resonance of the inverted pendulum, the big tower. And then here are the resonant peaks that come from the coupled modes. You don't just see the frequency of this and the frequency of this, but a normal mode, the lowest frequency of which represents all of the pendulum stages swinging together, and then various more antiphase combinations of those different stages. This is the most alternating set of motions, this peak right there. And this is fabulous, okay? This meets what I'm saying would be a good spec down to 3 hertz. It's great. So we really did not have to do any elaborate kind of physics thinking. There's tons of elaborate engineering here. But to understand what you're trying to achieve and how it would achieve your goals, the thinking is straightforward. Now, I will just show you the advanced LIGO isolation system only to indicate that it looks different in many details, but it shares many things in common. Here's a test mass. Here is it's suspended by a pendulum from this object, which is suspended by a pendulum from something that suddenly doesn't look at all similar to these cylindrical things, but we have, and that's in turn suspended from this. So we have 4 stages of pendulum-like isolation from something I will describe on Monday, an active isolation stage. In many ways, these share many similarities along with some other details that are quite different. And the initial LIGO isolation system was very crude, only worked well at frequencies above 40 hertz. But in moving to advanced LIGO, LIGO has caught up with Virgo and has something that works really well. Yes, Alex?
I know last time we were asking about why they look the same, the two bottom ones.
Oh, yeah.
And could there be a reason that just looking at the connecting the two,
Mm-hmm.
not be identical on the top and the bottom, so you have perfect parallel connectors, just makes the geometry really easy to connect those two, and then the second one is the one where
Yeah, and
does that affect anything?
it could. I should have a sharp answer for it. Anyone remember why LIGO went to the trouble of making that mass look so much like a mirror? I honestly don't. I mean, it is true what you're saying, and in particular, for thermal noise reasons, these fibers are made of fused silica, and it has to be very carefully welded and very carefully handled. And it is kind of natural to attach it up there, but I don't think it's required. So I'm not giving you the sharp answer why that design choice was made. All right, so let me show you where this ought to all come out. On this noise budget graph, and remember, this is an amplitude spectral density in displacement units, meters per root hertz, in a logarithmic scale versus a logarithmic scale of frequencies, and here's 10 hertz, and seismic noise calculated as the input times the frequency response of the system is coming down very steeply and doesn't quite meet the spec at 10 hertz, but by 12 or 13 hertz it does. Okay, and furthermore, you can see that it may never be the dominant noise source anyway. This is really sufficient seismic isolation. So there it is, and the steepness there comes from the many stages cascaded together. This bump, by the way, that you see both in the brown curve and the green curve isn't the pendulum resonance itself, because that's down at 1 hertz. This is at 10 hertz. This is the so-called bounce mode, the mode that comes from vertical motion of the mirror against the elastic stiffness of the glass fibers that support it. And it would be nice if it were lower, but there's reasons that we ended up with it stuck about there. Okay, let me say just a bit about radiation pressure noise. So here is a very crude sketch of a pendulum, a mass hung from some wires, and what the value added with this sketch, if there's any value added at all, is that what I want to point out is for the case of radiation pressure noise, the input is not to be thought of as a motion of the top of the spring, but instead as a force applied directly to the mass. Physics is almost the same. It's almost the same equation, but not quite. And now, something else that I will just assert, but you saw it on one of the first slides that Stefan showed you, that is that the spectral density of the force noise that is radiation pressure noise is white, which is jargon for frequency independent. Remember, there was that question, why did you make an explicit function of frequency when it's just a bunch of numbers? Okay, and he said because it's important that it's that same number at all frequencies. So we've applying as a force input to the mass a white spectrum, a frequency independent spectrum, and here is the equation of motion where instead of having an x output minus x input in the spring term, I've just got a force over there. Here is the frequency response output per force. It's got different dimensions because the input is different, but it's got the same frequency structure to the denominator. It's got exactly the same denominator. So this too will have a 1 over frequency squared roll-off above the resonance of the oscillator. So that's why Stefan could just say, okay, shot noise is white except for the filtering effect of the cavities, but radiation pressure noise falls like 1 over frequency squared. It's because that's the inertial response of the harmonic oscillator that is the mirror hung from a pendulum wire. And so, and that is the slope. We should be able to see that this is falling like 2 decades in displacement noise for 1 decade of frequency. Yes? Why does it have a, I'm sorry, could you say it does not have a characteristic frequency in the input power spectrum. It's completely white in the input power spectrum, but the response, the motion of the mirror in response to that white force spectrum has the characteristic frequency of the pendulum. Okay, that's where it comes in. All right, and Stefan is telling you much more and much more authoritatively than I could about radiation pressure and shot noise and the various quantum manipulations. I learned a ton listening to his first talk. I expect to be learning a lot more, and I hope everyone in the room is enjoying the treat of being able to hear him explain that. So I will leave that subject now and move on to another really important noise source that's also dear to my heart, the experimenters love their problems, right? So thermal noise is a terrible problem, and I love it because it's so interesting. It's perverse, but so be it. Okay, so I think it was maybe our first day together, if not the second, where I said, not only is seismic noise huge by this ridiculous factor, now we've seen how we can make that tolerably small. But Brownian motion is a whole separate question. And it's again the case that if I just think about the overall amplitude, the RMS of Brownian motion, the mirror's center of mass is moving by a huge amount, 3 times 10 to the minus 12 meters or thereabouts. And the motion of the mirror's surface with respect to the center of mass, not such a big factor, but still a number of orders of magnitude, it seems, above our target. And we have to ask, can we possibly detect gravitational waves in the presence of such huge motions of the mirrors? And recall that even though I solved my seismic noise problem by inventing a filter to put in between where seismic noise comes from, the ground, and the mass, I don't have that option here because this is what comes from any object being coupled to a heat path. Okay? So I don't have the same trick at my disposal for Brownian motion. So we have to see, how is it possible to make this tolerably small? So this is a rich enough topic that I've got a little sub-outline for this section. I want to talk about the original discovery of Brownian motion and tie that together with an idea that came much later, the mid-1950s, the fluctuation dissipation theorem. And then I will show how this plays out in interferometers, and in particular will focus on the most important thing you can manipulate to make thermal noise tolerably small, namely the amount of internal friction in the mechanical parts of the apparatus near the mirrors. So first of all, some history, and the organizers assigned me as my topic not just fundamentals but early history. This is really early, 1827. Other microscopists must have seen Brownian motion before Robert Brown discussed it in 1827, but it was Brown who realized that it was interesting. Okay? And I think this was because when the microscope was first invented, people were astonished, and rightly so, to discover what had never been known before, namely single-celled animals of all sorts that were swimming around like crazy. And for a long time, who cared if dust particles looked like they were swimming around too? We just weren't paying attention to them. But eventually, someone tired of looking at paramecia and whatever, and said, why is it that dust particles look like they're swimming even though I know they're not alive? And once he framed the question, people thought it was amazingly interesting, and they were right. There's a long history of what the speculations were about it that I don't have time to go into, but the solution did not come until 1905. Okay, it was a challenging problem. And who gave the solution in 1905? Einstein, okay? It's one of the things for which the Nobel Prize that he won was given, unlike relativity, which was not named in the citation. I won't defend that choice of the Swedish Academy of Sciences, but I will say that half of their judgment was right, that understanding Brownian motion was worth a Nobel Prize, okay? And too bad for Einstein that he did not only 3 things, but like 4 things that would be worth a Nobel Prize. Okay, here is the explanation that I'm sure everyone in this room has heard of, that namely, the explanation is that water is not a continuous fluid, but it is made up of chunks. We call them molecules. They randomly collide with the particles that are visible through a microscope, right? We've got three scales: the macroscopic scale, the things that are visible through a microscope, these dust particles, and then the things that are still invisible through a microscope, namely the water molecules. And because those are independent collisions, we get Poisson statistics again, basically, on the collisions, and sometimes there's a little extra kick in this direction, sometimes this, and raise your hand if you've ever looked at Brownian motion through a microscope. All right, enough hands, but too many hands weren't raised, so it's worth doing. It will drive you crazy. You will understand what had Brown exercised. All right, so I'm going to skip the history of Einstein's solution and why it took almost 80 years and someone the quality of Einstein to solve it, and instead give you a description in a form that was only written down in the early 1950s. This is the version of the fluctuation dissipation theorem that Callan and several of his collaborators wrote in a series of really readable papers. You can find them in the Physical Review from those years. So Callan wrote down this expression for the power spectrum, and this is a legitimate power spectrum and not an amplitude spectral density of, in this case, he wrote it in terms of the displacement of a mechanical object. I hope I will remember in a minute to say that it doesn't have to be that. All right, and he said that, all right, maybe it is a dust particle and you care about its spatial coordinate, and that power spectrum in general has this form. There is something that involves K Boltzmann T in the numerator. It's something that comes about from what heat is, random motion. It's got an explicit 1 over frequency squared in that prefactor, but then that whole prefactor is multiplied by this frequency domain object that in general has some interesting frequency dependence itself. It is the real part of a function called the admittance. And I will not assume that most people in this room have heard of an admittance, but if you have, that's great. So this is a frequency domain object, so it comes from the same kind of frequency domain algebra that we were doing before, but instead of using the position of the particle as the output, it uses the velocity of the particle. It's traditional. You could rewrite it other ways, but this is the tradition. So instead of x out over f, pay attention to v over f, and the real part of the complex frequency domain ratio of velocity response of a system to force input, the real part of that object is proportional to the amount of friction. This is an x out over x in transfer function. The dissipation shows up as an imaginary term, but when we pay attention to v instead of x, that switches things around, and it's the real part that that carries the information about the dissipation. I won't take my shoe off again, but this is why it's interesting that in this language there was in any language, there was a 90-degree phase shift between the motion of the top of the string and the motion of the shoe when I was on resonance. In terms of velocity, that's velocity being in phase with my applied force, and that's where I'm mechanically adding energy into the system. Okay, so real part of this complex function of frequency is where there's information about the dissipation, and it's that carrying along some non-trivial frequency dependence in general. That's what comes into the right-hand side that governs the strength of the thermal noise power spectrum. Yeah, time for a parenthetical remark before we carry forward to the real answer that we care about in gravity wave detection. One of the great joys of reading this set of papers by Callan is the delight he takes in saying, well, it doesn't have to just be mechanics. I can do this for electrical things. And we know there is an electrical form of thermal noise. It's called Johnson noise. I can also do it for optics. And he derives the Planck spectrum from this theorem. And on. He's got like 5 different examples from completely different domains of physics. All that's required is that we be talking about a system where you can define a displacement variable and a drive variable, and then you form an admittance that's appropriate to that kind of physics where you've got the ratio of the time derivative of the displacement variable divided by the drive variable. So this is an incredibly powerful theorem, not just for us. Okay? Now, this tells you that you don't have very many things at your disposal for affecting the level of this noise spectrum. Basically, you can make that factor in the numerator small. You could go to cryogenic temperatures. It's a lot of trouble. COGRA's working very hard on it now, and they are not going to get 2 orders of magnitude below room temperature, which means they're not going to reduce the amplitude spectral density even by an order of magnitude for all that trouble. Okay? Just saying. The other thing you can do, and this is what I'll focus mainly on, is trying to reduce the overall level of that admittance, of the real part of that admittance, by reducing the amount of mechanical dissipation. All right, but before we look at that in detail, I want to ask you to think, can this possibly be right? Because not many of us were taught the fluctuation dissipation theorem as physics students, but we're all taught the equipartition theorem. So let me remind you of what you already know about thermal noise, namely that each degree of freedom that satisfies some conditions that we won't bother to say what they are, has on average, it has an expectation value of the energy associated with that degree of freedom of 1/2 kT. Is dissipation mentioned anywhere there? No. How can that be? So, this is very simple. I should have made a expectation value symbol for this side. Sorry that I didn't. But anyway, it's really simple to plug in and say, if I know what K is for, say, a 10 kilogram mirror, I was thinking initial generation of interferometers when I did this, sorry about that, and 300 Kelvin temperature, the RMS motion of that 10 kilogram mass on a 1 Hertz suspension is 3 times 10 to the minus 12 meters, irrespective of the level of dissipation, only depends on the temperature. So how can I possibly be telling you the truth about thermal noise? Puzzled enough? Want a clue as to the answer? Here is the most remarkable figure from a paper ever written just to settle a bet. Okay? The guy who wrote this paper, R.V. Jones, a great experimental physicist, knew precisely what he was going to find, but some person who he thought was a jerk said that, no, that thermal noise doesn't work the way it actually works. And so Jones went to a lot of trouble to make this beautiful experiment. So let me show you what this is. This is 3 time records, 3 time series of the angular coordinate of a torsion pendulum. So something with a moment of inertia suspended from its center by a fiber. People used to see these things all the time. It used to be that if you were going to measure a small current, electrical current, you got out a galvanometer, which the most sensitive ones were vertical cylinders holding a still column of air around a very thin wire, and then a coil with a non-negligible moment of inertia and a little mirror also with non-negligible moment of inertia, and you put a current through the coil and it would torque with respect to some magnets, and light bouncing off the mirror, you'd see a spot move on the wall. Used to be the sensitive way to measure things. So people had them everywhere. And so by looking at where the light spot is on the wall, you could, by a suitable measuring apparatus, determine the angular coordinate of that simple harmonic oscillator. Now, here are 3 different records corresponding to 3 different amounts of mechanical dissipation applied to that torsion pendulum motion. Actually, they were adjusted by adjusting some electrical stuff, but at the end of it, it became different amounts of mechanical friction resisting the torsional motion. Now, are these 3 time records indistinguishable or distinguishable? I see a yes. That's not a good answer. Are they indistinguishable or distinguishable? Distinguishable. What is the distinction? Okay. There's a competition between dissipation and the oscillating. All right, but spectrum is a word that is sounding sharper to me, although I want to stay in the time domain. We'll talk in the frequency domain in a moment. But how about if we summarize both of those answers by saying something about the approximate functional behavior of these time series is recognizably different. This one in the middle looks the closest to a true sinusoid. For a cycle or two, it kind of looks like a sinusoid. This one, not so much. This one, hardly at all. Okay, so they are distinguishable. There is one very important aspect about them that is indistinguishable. What do all 3 traces share in common? Yes, or let me call it the RMS amplitude, okay, because at any given instant it might be large or small, but if you look over long enough time, you can see that the average amplitude is the same. What does that teach us? What was the equipartition theorem describing? The RMS amplitude. The RMS amplitude does not depend on the dissipation. It's the same physical system, same temperature, only difference was the degree of dissipation. Change the dissipation, you did not change the RMS. Okay. But you did change, who was it said spectrum? Someone over here said the word spectrum? Yes, good. All right, is precisely, if you want to use frequency domain language as I love, the spectrum that's different. So here, not precisely calculated from that figure, but just to illustrate the idea, is the power spectrum of 3 different oscillators with different degrees of dissipation. I can have a lot of dissipation and hardly see any resonant character at all. I can have less dissipation and see a more distinct peak, and I can have even less dissipation and have such a sharp peak that a time record would look pretty sinusoidal for a while. Now, because I'm stuck in my ways, to plot this on a log-log scale, you can't see by inspection that the integrals under those 3 curves are the same. But they are. The integrals under those 3 curves are the same, and the integral of a power spectrum is the mean square of the time series, and the equipartition theorem says that the mean square of the time series is 1/2 k Boltzmann T all squared. No, it's that without the square. Okay, so it must be the case if I'm describing a system like Jones measured, or like the fluctuation dissipation theorem is describing in general, that I've got the same integral, so I'm obeying the equipartition theorem, but now let's ask the question, if I go from a large amount of dissipation to a small amount of dissipation, how does the spectrum of the thermal noise change? As long as we look away from the resonance, then the less dissipation you have, the lower is the noise spectrum. It has to be made up for at the resonance, but that's fine or tolerable or work-aroundable. But if we find a way to only care about the degree of thermal noise far away from any resonance, then we can directly keep lowering it and lowering the amplitude of the noise spectrum as long as we can find ways to keep lowering and lowering the dissipation. So that's our charge. Can we find a way to suspend the mirrors in a gravitational wave interferometer with such a low level of mechanical dissipation that the degree of thermal noise in the system is small enough? So I will explain this in a few steps. One of the most important acronyms, this may be the only one-letter acronym that we have in our field. Mostly, Ligo at least uses three-letter acronyms. Does Virgo have a TLA system? TLA is three-letter acronym. It's a three-letter acronym for three-letter, okay? But this, Q, is the only one-letter acronym that I know. Stands for quality factor, and it's a dimensionless figure of merit to say how big or small is the amount of dissipation applied to an oscillator. It's a measure of the ratio of the elastic restoring force to the dissipative force, and I will show you a diagram, and well, let's do the diagram right here. So you can either spot it in the frequency domain or the time domain. Here's a frequency domain transfer function of an oscillator. The Q is either the ratio of the resonant frequency itself to the full width at half max of the resonance peak. Less dissipation makes a sharper peak, so it makes that denominator smaller, and less dissipation corresponds to higher Q. You can also read it off of a transfer function or frequency response as simply the ratio of the height of the peak to the low frequency limit, gives the same number. Or if you happen to kick an oscillator and watch its damped oscillatory ring down, if you find the damping time and multiply by the resonant frequency and multiply by pi, you also get the same number. Three different ways, whatever is most convenient to you. Yet another way that I should have sketched, if you drive an oscillatory system with an oscillatory input far from resonance, you will see a small phase lag. You won't see perfect phase agreement between force and displacement, and the angle in radians by which there is an offset between force and displacement is 1 over the Q. So that's yet another way. Now, we have to have it's a dimensionless number. I have to tell you what dimensionless numbers are good and what are bad. We want big numbers. The bigger the better for most purposes. There are some problems with big numbers that you have to tolerate. The best Qs I know that we know how to achieve in mechanical systems are of order 10 to the 8. Anybody can build an oscillator with a Q of 10 to the 3 with just the most minimal of trouble. And you don't have to be as good as us, but you have to pay some care, and then you can get a Q of 10 to the 6. So Q of 10 to the 8 is the kind of thing we tend to be looking for when we can get them. And something that I also want to point out, again, I've been mentioning it from the beginning, is we've got a number of different modes whose thermal noise we need to think about. Most obviously is the mode of center of mass motion of the mirrors, the pendulum mode. But there's a huge spectrum of other modes. The most important set of other modes are the set of internal modes of vibration of the mirrors themselves, and there's a huge number of them. It's a really crowded spectrum, so crowded that you should not make the mistake, as I used to make, of thinking that, oh, the lowest one or two is good enough. It's really the whole superposition of a very complicated spectrum. Now, why am I belaboring this point? They all have sort of a universal shape of noise power spectrum, but we see them in two different regimes. There's a logarithmic frequency scale, and the pendulum mode is going to be typically around 1 hertz. If you engineer your mirrors correctly, then the farthest of resonant peaks associated with internal vibrations of the mirrors will be roughly in the range of 10 kilohertz. This is not just an accident, but is very much by design, because what we're trying to do is come up with as broad a frequency range as possible that is not contaminated by the thermal noise associated with the pendulum mode, nor is it contaminated with the thermal noise associated with those internal modes. Because, recall what we're doing when we reduce the dissipation is we're putting all of the half kT's worth of energy in the peak. So the frequencies of every resonance are going to show up as huge things in our measured power spectra. But if we banish them to frequencies so low we don't care about them, so low that our seismic isolation doesn't work well, or high enough that we don't care about them, I kind of think high frequencies would be interesting, but we just declare, okay, I put them there because I don't care about frequencies that high. Then all we have to do is worry about the high frequency tail of the 1 hertz pendulum mode, and the low frequency tail of the various internal modes of the mirrors. And anticipating what you all are going to learn about data analysis from Alan Weinstein next week, I think, let me suggest that it's quite possible to do interesting physics with a gravitational wave detector, even if there are huge resonances, so long as those resonances are far enough away from signal frequencies. And I will diagrammatically prove this to you twice. That is supposed to represent a small signal in the presence of large noise at low frequency. Can you detect that signal? Yes. Okay. And if you were going to do it mathematically, you would filter this out and whatever, but your eye, you can see that, even though its amplitude is small. How about this? This is a high frequency resonance. Do you see a signal? Yes. Okay, so we have not ruined our prospects for detecting things in this broad intermediate frequency band by failing to get rid of all this noise. It's sufficient to banish it to frequencies outside of places where we expect to be able to do good searches. So that's what we're doing by finding ways to reduce the dissipation so that we've got a very sharply peaked spectrum with very low wings. Okay, so if we do a really bad job external sources of dissipation would dominate. Like if we didn't sufficiently pump the air out of our vacuum chambers, or if we let pendulum wires rub in a clamp, or if there were strong magnetic fields next to conducting test masses and their eddy current damping, we could ruin our prospects. But we know that, and so we won't, okay? Any good craftsmanship eventually finds and eliminates all such excess external dissipation from our systems, and we're left with internal friction in the properties of elastic materials out of which our apparatus is made. And I'll say more about that, but once we use our good craftsmanship, then the challenging part, this can be challenging at the from time to time, but the real challenge is to find ways to make the internal friction, the internal dissipation in test mass materials and pendulum fibers, make it small enough. Now, I need to say a few things about how internal friction works, because I never learned this in my physics training, right? But it turns out to be really important. I became, in effect, a material scientist for a decade or more of my life, even though I wanted to be, you know, a co-discoverer of gravitational waves. I wanted to be doing relativistic gravity. But material science turned out to be the challenge. So, remember that friction coefficient B, Bx dot, that's how we're all taught to model friction. It's a terrible model for internal friction in materials. There is no material that I know of that over any substantial frequency range obeys velocity damping. Okay? Over small ranges, okay, but really not. And you know it must be the case because we could not build xylophones and carillons if it were the case, because you can make high Q acoustic resonators over a huge range of frequencies, but if it was velocity damping at those high frequencies, those high notes on a xylophone would sound dead. But they don't, which proves that dissipation isn't mainly a velocity damping effect. Now, if you read the material science literature, you will be told that, of course, we know that velocity damping is not a good model. Here is the good model for internal friction. It comes from something called anelastic relaxation. And the sources of anelastic relaxation typically are defects in materials that have their equilibrium positions depend on how much internal stress is applied to the system. A dislocation sits between one chain of atoms, but when you flex it, the dislocation slides across a number of rows of atoms. Or there's a point defect that hops from one place to another when you flex the material. And the kinds of models that material scientists tend to make for that kind of dissipation end up having the kind of frequency response that you would associate with this kind of model. You say, all right, a real spring is an ideal spring supplemented, unfortunately, by another unit that's a really weak spring in series with a dashpot. That has a particular frequency at which the dissipation is strong, and as you go away either to low or high frequencies from that characteristic relaxation frequency, you see a decrease like 1 power of frequency in either direction. So the exception to my statement that nothing looks like velocity damping is on the low frequency side of a strong relaxation, you see the dissipation growing like a power of frequency. That's the one case where it's kind of true. But if you pay attention, you can basically always see that there's a characteristic frequency here. Note, this is an interesting side effect, that it has to be the case that the low frequency stiffness and the high frequency stiffness of materials are different from one another. Because at high frequencies, you're stretching both springs. At low frequencies, you're only stretching the ideal spring. This is a mechanical example of the Kramers-Kronig relation, if you want to think of it that way. Now, it gets worse. Well, okay. The trouble with this, it took us in the business a long time to figure out, is that most materials don't show just one or two really strong relaxations. There is one that we encounter a lot. It's called thermoelastic damping. It's not really microphysics at all. It's got to do with the temperature dependence of the coefficient, or the frequency dependence of the coefficient of thermal expansion, and that turns into, you flex something, it gets warm on one side, cool on the other, heat flows, you let it relax, and you don't get all the elastic energy back. It's got some dissipation. So you can see often in flexing fibers a relaxation peak from that effect. But it's not very universal. Here is the quasi-universal statement. And this is utterly astonishing. And it's suppressed in the material science literature. It's too upsetting to material scientists. That is, there is such a large spectrum of relaxations with different relaxation times in most materials that the best simple model you can apply to any material is that it's got a frequency independent level of damping. You can describe a given material by saying, oh, that material has a Q of about 1,000. And that would be true for, say, aluminum or something, or steel, or tungsten. They all have a Q of about 1,000, and it doesn't matter at what frequency I measure it. Okay. And here are the numbers. Okay. Most metals that you would go to a supply room next to a machine shop, around 1,000. Really highly damped materials like rubber, 10 to 30. Crystals in the hundreds of millions, but now here is the miracle. This is the material science miracle that made gravitational wave detection possible. Fused silica, ordinary, well, not ordinary glass, good quality glass, such as you would buy from the top quality optics manufacturers, and ask specifically for the ones with the least impurities. When you have the purest SiO2 glass, it shows a Q of, if you handle it carefully, 200 million. Think of this. Is glass a crystal? No, it's amorphous. Everything in it is a defect. It's entirely made of defects, by a crude way of describing it. That's not the way a glass physicist would describe it, but it is as low in internal degrees of freedom that can cause internal friction as the best low defect crystals. And if this hadn't have been the case, we would not have succeeded. Okay? We've gotten a long way piggybacking on the optics industry that learned how to make good mirrors out of good glass. And if we'd had to go to sapphire crystals from the beginning, or silicon crystals, okay, I don't know when we would have succeeded. You're laughing because you all believe in sapphire, or? Okay. Okay, so nature gave us this miracle, and it's a very specific miracle. If you go to temperatures substantially different from room temperature, glass doesn't have this property. Okay? So acoustic frequency range at 300 Kelvin, glass is essentially perfect for our purposes. And who ordered that? I mean, we wanted it, but it was given to us as a gift. Let me summarize what we've learned. What are the rules by which one can make a sufficiently low dissipation pendulum suspension and sufficiently good mirrors so that the thermal noise, both from the pendulum peak at low frequencies and its high frequency tail and the low frequency tail of the internal modes, are low enough. Use fused silica fibers and use the best quality fused silica for the test masses. And then you end up where we're stuck today, which is a pretty good place, but won't be good for 3G. It turns out that we are not dominated either by the thermal noise from the pendulum mode, nor from what you would think would be the noise of these internal modes, if their dissipation were really governed by the glass out of which the mirrors are made. Instead, it's the thin dielectric coating that makes ultra-high reflectivity mirrors that dominates the dissipation in our mirrors and means that we are only a little way from having to worry about it. So here we are. The green curve represents the thermal noise as calculated. And you can see it's got some complexity to it. Here is the thermal noise that comes from all those high frequency peaks. It's a very shallow power law. Here is the steep power law associated with the high frequency tail of the pendulum thermal noise. There's an extra bump in here for that bounce mode. We won't worry about the pendulum mode for a while or ever. But doesn't take much more improvement beyond, in fact, by the time, as Stefan showed us this morning, by the time we hit the target sensitivity for the advanced detectors, we will have bumped up against the thermal noise that's driven by the dissipation in the coatings. And so there's a huge amount of very urgent research on making lower dissipation coatings to enable interferometers to advance beyond the 2G targets and into the 3G land of the future. So that's all my material for today. Any other questions before we break and get ready for the World Cup? Yes? Ah, yes. Okay, yes, I should have mentioned them, and they are surely here. So, there's a lot of spikes in the spectrum. They come from several different places, but let's talk about this because it's the most interesting. So 2, 3, 4. This is a vibration peak that, if you actually zoom in, resolves itself into 32 peaks, I think. That has to do with the fact that each suspension fiber on each mirror do not do this. If you were to break every rule in the book and pluck that fiber, and if you did it gently enough that you didn't break it yet, it would vibrate. These are called the violin modes, and that is the fundamental, the mode that has nodes just at the end and an antinode in the middle, but then it's got a harmonic spectrum, so that's 500, here's 1,000, 1,500, 2,000, and so on. If things are good, then those will only be driven at their Brownian motion amplitude. Now, you would think, okay, it's not the mirror vibrating, but it's the things that are attached to the mirrors, and there's recoil, because when the middle of the fiber moves forward, the mirror has to move backwards. It's a big mass ratio, so you get a big dilution effect from the fact that the mirrors used to be 10, now 40 kilograms, okay, and the mass of the fibers is pretty small, but it's enough to see. And it violates our design rule that we're supposed to put all resonances outside the signal band. Nobody's figured out a good way to have a low enough frequency pendulum mode with light enough fibers that will not drop the mirror, okay, because what you'd want to do is, how do you make these go to high frequencies? Make the fibers short, not so good, or make them ultra light. That would be good, except they need to be sturdy enough to support the weight. So those violate our design rule because no one could see a way to obey the design rule, and they're kind of a pain. You have to notch them out of the data before you analyze it or do other horrible things. But they're horrible things that can be done and that don't actually ruin the sensitivity. in large measure because they're high enough Q that they are concentrated. But the fact that there are multiple fibers and multiple masses means that they're not that concentrated because each of those supposed modes is actually a small forest of modes. So yes, I was trying to shield people from some of the ugly truths, but thank you for that question. And anyway, okay, any other questions before? Yes. Mostly noise in the control loops associated with aligning various mirrors. And because that seems like, why is that even involved? That means there's hope for making it a lot smaller with better engineering. Okay? The fear is that in addition to that set of noise terms, that there's also some noise in at least a part of this band from scattered light, and taming scattered light and making sure that the small amount of light that doesn't reflect specularly from our mirrors but that scatters to the wrong angles, if that scatters back into the beam and falls on the photodetector, that can bring in, even at very small electric field amplitudes in that amount of light, really big phase excursions, and can end up with, when we're looking at 10 to the minus 10 radians, it can cause huge problems. And in principle, you can always run it down and find all the scattered light and find ways to block it, but it's a problem that quickly runs through your fingers. So that's the fear, that maybe some of this unexplained noise in here might be from scattered light. Any other questions? Yes. Yes. Let me say it in language that is as close as possible to the way Stefan was describing it this morning. The shot noise, which that is a frequency-independent spectrum in the natural units, either in units of brightness fluctuation, or if you look after you've turned an amount of light into a photocurrent in the current out of the photodiode. So it is intrinsically white if you use the right units to describe that physical effect itself. However, what we're plotting here is the amount of mirror motion it would take to give an equivalent signal. And since if you move the mirror in a Fabry-Perot cavity, if you move it at high enough frequency, you don't get as much phase change as if you did it at a low frequency. That means that if you take something that's white and re-express it in terms of mirror motion, you need more noise, or that a given amount of noise looks like more motion in a frequency range where you're insensitive to the motion. So the fact that the Fabry-Perot cavity kind of averages over motion that's higher frequency than its so-called corner frequency gets turned upside down, and that averaging over, because it gets put in a denominator, boosts up something that's white in its natural units when you express it in terms of effective displacement units. Okay. Anything else? Okay, so we reconvene here at 4 p.m. for the game.